Good evening.
Yeah, hello Lalita, good evening.
Good evening.
Good evening. Okay, so let us start week 6 session. Hope everyone quiz is good. Any doubts from quiz 1?
Can we ask few questions?
Regarding quiz 1,
Yeah, the quiz one.
yeah, later we can discuss. First we'll do week 6 summary
Okay,
and then, yeah,
okay, no problem.
yeah. So how many of you have gone through week 6?
Not it.
Okay, not it. Yeah, okay. So coming to what is normalization and schema refinement or schema refinement. So my voice is clear, right? Is it audible properly or is it bit low or anything? It's
Yes, ma'am, it's audible.
okay. Yeah. My screen is coming right. It is visible.
Yes, ma'am, it is.
Okay. So yeah, let us start. So what is normalization or schema refinement? Normalization or schema refinement is a technique of organizing the data in the database. It is a technique for organizing the data in the database. So, it is a systematic approach of decomposing tables to eliminate data redundancy and undesirable characters. So, it is a systematic approach of decomposing the tables to eliminate data redundancy and undesirable characteristics. So, these are some of the what anomalies: insertion anomaly, update anomaly, and deletion anomaly. So, we'll see these anomalies. What does this anomaly means in the coming slides? Okay. Most common technique for schema refinement is decomposition. So most common technique for refining our schema is decomposition. So goal of the normalization, why what is the goal of normalization is to eliminate redundancy. What does redundancy means? Redundancy means it refers to repetition of the same data or duplicate copies of the same data stored in different locations. So it is nothing but repetition of the same data or duplicate copies of the same data stored in different locations, like in the multiple locations same data is stored. So normalization is a technique and it is used for mainly two purposes. It is used mainly for two purposes, like eliminating redundant or useless data or ensuring the data dependencies make sense, that is data is logically stored. So data, the normalization does main purpose is to eliminate the redundant data and to ensure the dependencies, whatever dependencies the data has, that makes sense. Okay. So that these are the anomalies, right? Update anomaly, insertion anomaly, delete anomaly. So what does this anomaly mean? So let us consider this table, employee table. Here see employee table. Here it has employee. You can see employee ID, it has employee address and skill. So if you see the records stored in the employee skills table, see employee ID is repeated, like 426, 426, 519, 519. So employee ID is alone is not the primary key. And coming to the employee address, as 426 is the same employee, his address should be same, like 87 this address. And 519, you can see 519 address is different. It is different for one in one record and in the other record it is different. So this is update anomaly. So if we have multiple IDs, multiple employee IDs with the same ID, like 426, 426, then when we update, if skill has to be updated for this employee ID 426, Okay, then we should update here. If the address of the employee has to be updated, we should update 4 to 6 employee address in both the records, in first and second record. But while updating 519, we just have updated first record and forgot the second record. So if we have multiple employee IDs with the same ID, then we have to update wherever the employee ID for that particular employee ID. But this has missed. So this is called update anomaly. Employee ID 519 is shown as different address on different records because while updating it has got missed. Okay, this is update anomaly. What does insertion anomaly mean? Until here you can see this faculty table. If you see the faculty table closely, then the faculty has ID, name, faculty hiring rate, and course code. Okay, if we have to insert a faculty, then if he has not assigned to any course set, if he is new joinee and if he has not assigned to any course set, then we won't be able to insert that faculty because he has not taken any course. So this is insertion anomaly. Until the new faculty member, some new faculty member, here it is Dr. Newsome, is assigned to teach at least one course, his details cannot be recorded. If he has not assigned to teach any course, then we cannot store his record in the table. This is insertion anomaly. And deletion, what does deletion anomaly means? Okay, when we see, let us see here the same table, faculty table only. It has name, ID, height, date, and course code. All the information about the particular faculty will be lost if he temporarily, if he has stopped taking this course, then his complete information will be lost. If we delete this course code for this particular faculty, the complete record will be lost. This Dr. Giddens information is lost. All the information about the Dr. Giddens is lost if it temporarily ceases to be assigned to any course. This is deletion anomaly. Okay. So what is the resolution for this? The thing is, we can decompose our schema. This is current schema, right? Employee skills, we can decompose it. The faculty also we can decompose, like faculty information in separate table and course information in separate table we can do. So somehow like decomposition of the tables will, this is the resolution to avoid this anomalies is to decompose our schema. Okay, we can decompose our schema, this employee schema as ID and address as one table, and ID and skill we can store in the other table. So for this, like 4 to 6 we can store 8 7, this address. For 5 and 9 we can store the one address only. There is no need to maintain several records for the same employee to store at table. Okay, insert also this kind, for this also this table, this schema, faculty schema can be decomposed into two tables that store faculty information separately and course information separately. So ID, name, hire date of the faculty can be one table, and ID of the ID and course can be in the separate table. Same decomposition will eliminate the deletion anomaly also. Is it clear? Yes or no?
Yes, ma'am.
Okay. Yeah, you understood now what is the purpose of decomposition and what is what does normalization means?
Yes, ma'am.
Okay. What are the desirable properties of decomposition? So if we decompose a schema to several tables, then what are the properties, desirable properties of our decomposition? So the decomposition must be lossless join decomposition. That means we should not miss any information. It should be possible to reconstruct the original table. By having the decomposed table, we must be able to reconstruct our original table. So our decomposition should be lossless joint decomposition. This is one of the desirable property of decomposition. And the other property is dependency preserving property. So the decomposition should preserve the dependency as well. So it should be dependency preserving as well. So that means no functional dependency or other constraints should get violated. So these are the desirable features we want when we decompose a table to different tables. Okay. So what happens when we decompose our table? So original schema can be decomposed to different tables to achieve 1NF or 2NF or 3NF, this kind of normal forms. Okay. So let us see what is a normal form. A normal form specifies a set of conditions that original schema must satisfy in terms of its constraints. So these are the normal form is nothing but it specifies the set of conditions that the relational schema must satisfy in terms of constraints. Let us say like 1NF, which is a first normal form. In this normal form, we should not have any multi-valued attributes in our table. So this any normal form will specify a set of conditions that a relational schema must satisfy in terms of constraints. They offer varied levels of guarantee for the design. Okay, these normal forms offer varied levels of guarantee for the design. So normalization rules are divided into various normal forms. Most common normal forms are first normal form, second normal form, and third normal form, which are also called as 1NF, 2NF, and 3NF. Okay. Informally, a relational database relation is often described as normalized if it meets third normal form. A database relation is often described as normalized if we say a table as normalized if it is in 3NF. Most 3NF relations are free of these anomalies, insertion, update, and deletion anomalies. Most of the 3NF relations are free of these anomalies, but they have some redundancy. But 3NF also has some redundancy. We'll see that also. And these are the additional normal forms: EKNF, elementary key normal form. We will see only 1NF, 2NF, 3NF, BCNF, and fourth normal form. The other normal forms we won't be seeing. Okay. Bose-Einstein normal form, which is also called as BCNF, multi-valued dependencies, and fourth normal form. Essential tuple normal form, ETNF, joint dependencies, and with this we are not going to see this normal form. Just know these normal forms also exist. Okay. So what is first normal form? I think you all know, right? Anyone of you can please describe what is first normal form?
It doesn't have multi-valued attributes, ma'am.
Yes. Yes, it won't have multi-valued attributes. A relation or a table is in 1NF first normal form if and only if all the underlying domain contains atomic values only, does not have multi-valued attributes. So here example you can say student table. Student table, it has SID, S name, and C name. Is it in 1NF? Is a student table is in 1NF? This table, the student's table, is it in 1NF?
Ma'am, course name has multiple courses under it, so no. Multiple
Yes.
values.
Yeah. So the C name, this attribute has multi-valued, multiple values. So C comma C plus plus, that kind of thing we should not have. So this is not in 1NF. What is primary key here? Primary key is SID. SID itself is a primary key for this table. Okay. But it has multi-valued attributes and it is not in 1NF. Okay. What happens if the schema is in 1NF? Some kind of queries will be difficult to, yeah. If the following table has to be made into 1NF, then what we can do, we can write this multi-valued attribute separately for each record. Like C can be in one record and C++ can be in another record. So this kind of relation is in 1NF. It does not have any multi-valued attributes. You can see each and every record is unique. Each and every record is unique. So S1 A C, S1 A C++, each and every record is unique, right? There is no redundant records. each and every record is unique, and there are no multi-valued attributes. So this is in 1NF. And what is primary key here? SID is not primary key here. SID is not primary key because all the values are not unique. You can see S1, S1, S2, S2. So this is not in 1NF. This is not primary key, sorry, this is not primary key. But what seen in and SID together will form the primary key. So S1C, S1C++, this together will form the primary key of this table. Okay, let us see. Yeah, what is the possible redundant? This is also in 1NF. You can see it has each and every record is unique and there are no multi-valued attributes. So this is in 1NF. But what are the drawbacks for this table, the supplier table? So you can see the drawbacks of 1NF. So deletion anomaly. If we delete this row, S340 row this row, then what happens? We will lose. Then we lose the information that S3 supplier S3 lives in rotor. Okay, and the drawback of 1NF is it also has insertion anomaly. We cannot insert a supplier S5 located in kernel until S5 supplies at least one part. So we cannot record any supplier information if he has not supplied any part. So this is insertion anomaly. Update anomalies: if supplier S1 moves from Delhi to some other place, Kanpur, then it is difficult to update all the tuples having SID as S1 and city as Delhi. So we have to update if some SID has shifted, the supplier has shifted to some other city, Kanpur. So here, wherever S1 is there, supplier S1 is there, we have to update everywhere from Delhi to Kanpur. So this will, if we miss anywhere, this will lead to anomaly. Okay. So 1NF has insertion, deletion, and update anomaly. So normalization is a method to reduce redundancy. So however, sometimes 1NF increases this kind of anomaly, this kind of redundancy. So you can see the information is redundant. S130 Delhi, S130 Delhi. So we are storing the same information in multiple records. You can see there is redundancy in our table, in our data. So somehow 1NF has redundancy, like lot of redundancy, and there is this anomalies also. Deletion: if we wanted to delete and if any record is deleted, then we will lose complete information of this particular supplier. And insertion: whenever we are trying to insert a supplier, then the supplier must have supplied any part. If he has not supplied any part, then we cannot insert that supplier information. And if we have to update any supplier information, then we have to update in all the places where that particular supplier ID is there. So this kind of anomaly is also there, and there is redundancy also in 1NF. Okay. When redundancy is possible in 1NF? When LHS is not a super key. When LHS is not a super key, here let's say if the dependency, let X determines Y be a non-trivial FD. That means Y, that means X determines Y, right? So here beta, Y is not subset of X. Okay, let X determines Y be non-trivial functional dependency. That means Y is not subset of X over R. With X is not a super key of R, then redundancy exists between X and Y attribute set. So if X is not a super key, if this attribute is not a super key, but it is determining another attribute, then the redundancy will be there between X and Y. Here the same example. Here X is not a super key. If we write X determines Y, so 1 3 1 3 2 3 2 3. Let us see. For every one there is 3. For every one there is 3. For 2 also there is 3. 4 4 6. Okay. Here X determines Y. But the thing is, X is not a super key. You can see X is not a super key. It is not a key. It is not a super key. And you can see the redundancy is there. Okay. If X is not a super key for functional dependency X2, X determines Y, then redundancy will exist in 1NF. Hence, in order to identify the redundancy, we need not to look at the actual data. It can be identified by the given functional dependency. Okay, if the redundancy is present or not in our relation, it is not required to look at to a table. By seeing the functional dependency alone, we can say whether redundancy is possible or not. So let us see the functional dependency x determines y. Here x is not a super key. Then redundancy will exist between x and y. The same thing here. It is described using the example. And if LHS is a super key, if X is a super key, then redundancy is not possible. If X determines Y is a non-trivial FD over R with X is a super key of R, then redundancy does not exist between X and Y attribute set. The same example you can see X determines Y here. For 1 it is 4, for 2 it is 3, and for 2 it is 6, and for 3 it is 4. And here X determines Y. Like you can, if there is exist another attribute also, like X determine, here it is X determines Y determines X is false, because for 4 it is first it is 1, and for 4 here it is 3. For the third record you can see Y determines X is false, but X determines Y is true. But you can say the data is not redundant because X is super key here. X values are unique. It is a super key. That's why there is no redundancy here. If LHS is not a super key, then redundancy will be there. If it is a super key, then redundancy won't be there. By seeing the functional dependencies alone, we can say whether our redundancy is possible or not. Then coming to the next normal form, which is second normal form. A relation R is in second normal form only if R is in 1NF and R contains no partial dependency. So when we call a relation is in 2NF, it must be in 1NF and it should not have any partial dependency. So what does partial dependency means? Any one of you? Any idea what is partial dependency?
No, ma'am.
Okay, let us see. So let R be a relational schema and X, Y, comma A are attribute sets of R. You understand, this terminology. R is our table and it has some columns. X, Y, A are its attributes sets over R, where X any candidate key, Y proper set of candidate key. So X is a candidate key. X is a candidate key, and Y is proper subset of candidate key. That means, so Y, okay, let us say X here is something like some ID, employee ID, comma employee name. Together is a candidate key. Then Y can be like employee name. So Y is a proper subset of candidate key, and A is a non-prime attribute. So that means A is not present in any candidate key. So if Y determines A exists in R, then R is not in 2NF. So here Y is part of candidate key. And if it is determining any other non-prime attribute, then we can say R is not in 2NF. So let us take the example here, same thing. Employee ID, I am writing it as EID, and ename. This together, let us say this together are candidate keys, and there is one non-prime attribute, let us say salary. Salary is non-prime attribute. Here it is A, and this together is X. This together is X, which is our candidate key, and Y is part of candidate key. So Y can be employee ID or Y can be employee name here in this case. So if Y is determining any other non-prime attribute, let us say employee ID determines salary also, then this relation won't be in 2NF. So Y is here, employee ID is not candidate key. It is proper subset of candidate key. It is part of candidate key and it is determining the other non-prime attribute salary. Salary is not in candidate key. It is not prime attribute. What are prime attributes here? Employee ID, employee name are prime attributes. Employee ID and employee name together form the candidate key. Y is nothing but part subset of the candidate key, which is employee ID. Here it is determining other non-prime attribute, which is salary, and this kind of dependency is there in our relation, then we can say this relation is not in 2NF. If this kind of dependency is there, then we can say the relation is not in 2NF. If Y determines A, that means the subset of candidate key is determining any other non-prime attribute in our relation, then we can say R is not in 2NF. So Y determines A is a partial dependency. That means a part of our candidate key is determining non-prime attribute, which is called partial dependency. So Y is proper subset of candidate key and A is non-prime attribute. Okay, what is a prime attribute? A prime attribute of a relation is an attribute that is part of candidate key of the relation. So here, employee ID, employee name are prime attributes. This is our part of our candidate key. And salary is not part of our candidate key and it is called non-prime attribute. And if the part of candidate key or proper subset of candidate key is determining any other non-prime attribute, then we can say that relation is not in 2NF. Is it clear? What is the condition for 2NF? Clear, no?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay, let us take here. Let us see the same thing with an example. So student has these attributes SID, SNAME and CNAME. And you can see this is in 1NF, right? This is in 1F and 1NF. Each and every record is unique and there are no multi-valued attributes here. And is it in, what is primary key here? SID and CNAME together will determine the SNAME. So it is a primary key. This is already in 1NF and the dependencies possible are, so you can see SID, CNAME together will determine SNAME, student name, and SID alone can determine student name. Student ID alone can determine student name. And SID and course name together will determine SNAME, student name. So here SID alone cannot be primary key. Here you can see the SID is repeated. It is not unique. So it is not primary key. It is in 1NF, but the relation is not in 2NF. You can see here, there is this partial dependency exists. So SID, CNAME together are primary key, but part of primary key, which is SID, is determining other non-prime attribute SNAME. So this relation is not in 2NF. Okay, because of the partial dependency, this partial dependency. Okay, now what we can do? If the relation is not in 2NF, then we can decompose our table. So how to decompose our table? We can make SID, SNAME in one table and the remaining thing, SID and CNAME in the other table, we can decompose. So here in the relation R1, you can see this relation, in the relation R1, you can see SID is a primary key, and here what is primary key? SID and CNAME both together from the primary key. So this relation is in 2NF. There is no partial dependency. You can see here SID in this relation, SID is primary key and it is determining SNAME. Okay, that is, it is candidate key and it is determining the other attribute, no problem, non-prime attribute. Here SID, CNAME together are primary key. It has no like functional dependency, no functional dependency for this table. So this is in 2NF and it is lossless join. It is lossless join. If you perform natural join of these two tables, then we will get this table. So it is lossless join in 2NF and it preserves the dependencies. It preserves this dependency also, this dependency. So the 2NF will preserve whatever the tables we are decomposing, they will be lossless join decomposition and they preserve dependencies also. Okay. Is there any redundancy in our table? Yes, there is redundancy. You can see what this information S1 is storing C multiple times. There is some redundancy. There is some redundancy in our table. And while updating here, like some kind of anomalies also will be possible because there is redundancy. So you make it in updation anomaly is also possible. Yeah, some kind of anomaly is also possible here. Okay, the same example you can see for 2NF only. There is one more example, the supplier, the thing previously we have seen a supplier relation. It has SID. This is in SID, status, city, PID, quantity. It is in 1NF. You can say it is in 1NF. All are like unique. All records are unique, and there are no multi-valued attributes. And what are the possible dependencies here? What is key here? SID and PID together will form the key. SID and PID will together form the key. And what are the partial dependencies possible here are SID determining status. You can see SID for S1 it is 30, 30, 30, 30. For S2 it is 10. For S3 it is 40. For S4 it is 30. So SID determines status is true. So SID is part of primary key, candidate key. It is determining non-prime attribute status. So this is partial dependency. So this relation is not in 2NF. And the other possible partial dependency is SID determining city. So it is S1 Delhi, S1 Delhi, Delhi, Delhi. So it is like S1 determines city is true. Whether P1 determines quantity, whether P determines quantity, no, right? P. So for P1 it is 100, for P1 it is 245. So P1 determines quantity is false. Okay, these are the possible partial dependencies. SID and PID together is the key, but SID, part of primary key, is determining other non-prime attributes. So it is partial dependency. And what we can do, the relation is not in 1NF, not in 2NF. So we can decompose it into two tables. Supplier, for supplier, one table you can maintain, and for supplier city, we can maintain one table. For supplier quantity, another table. Okay. So these are the dependencies, right? We can decompose into two tables like SID, status, city in one table, and SID, PID, quantity in the other table. These are the partial dependencies. We can we can we can decompose these attributes in one table like SID, status, city. We can create for these attributes. We can create one table, and for the other attributes SID, PID, and quantity, we can decompose it into another table, quantity, supplier quantity. So now SID determines status, that is valid because SID is primary key for this table. For this table, SID is primary key. So SID determining status is valid. This is not partial dependency yet after decomposition. And SID determining city is also not not partial dependency. And SID PID together determines quantity. Oh, that is also valid because for this relation SID and PID is the candidate key. This dependency is valid. And this schema, the decomposed schemas are in 2NF. But what are the drawbacks? It also has drawbacks. Deletion anomaly is there, insertion anomaly, update anomaly is there. So if we delete a tuple in supplier city, if we delete a tuple from the supplier city, then we will lose the information about the supplier, but also lose the status value of that particular city. So we will lose if the supplier, if the particular, let us say this has in one table, and what we will have in the decomposed table, we will have S130 Delhi, only one record. We no need to maintain these multiple records for S1. For S1, S2 10 kernel we can tell. And if we wanted to delete a supplier, a tuple from the supplier city table, this table, then we not only lose the information about the supplier, this supplier information we will lose, but we will also lose the status, this 30, this 10 value for that particular city. For Delhi, the status is 30. For kernel, status is 10. That kind of information we will lose if it deletes any record. Insertion anomaly, we cannot insert a city and its status until a supplier supplies at least one part. So this is for this table. And update anomaly, if the status value for a city is changed, then we will face the problem of searching every table for that city. If the status value is changed, then we have to update everywhere. So that's kind of thing also will be there. Okay. After here it is shown after decomposing, only the deletion anomaly is described, while before decomposing you can say insertion anomaly, update anomaly also persist. Okay, 2NF also will have redundancy, and it will also have some anomalies. Like example here is deletion anomaly. But 2NF decomposition is always lossless join decomposition, and it also preserves the dependencies. So coming to the other normal form, which is the normal form, let R be in relation schema with the relation schema. R is in 3NF only if R should be in 2NF. It should be in 2NF, and it should not contain any transitive dependencies, or every non-prime attribute of R is non-transitively dependent on every key of R. So there should not exist any transitivity dependencies. What does transitivity dependency means? Non-prime attribute determining another non-prime attribute. This kind of dependencies is called transitivity dependency. That we will see how we will get that dependency. But if we have this kind of dependency, non-prime attribute is determining another non-prime attribute, then this schema won't be in 3NF. It won't be in 3NF. So it should be in 2NF. First it should be in 2NF. That means partial dependencies it should not have, and it should not have transitive dependencies also. That means non-prime attribute should not determine non-prime attribute. Okay, alternatively, we can define 3NF in this way also. Alternatively, R is in 3NF if for each of its functional dependency, X determines A, at least one of the following conditions holds. If we have some functional dependency, X determines A, and at least one of this condition should hold. X contains A, that means A should be subset of X, that which is a trivial functional dependency. So if we have something like employee ID, comma employee name determines employee name. This is trivial, no? This is trivial because employee ID and employee name together determining employee ID is trivial because employee name is part of this our X. If this kind of thing exists, then okay, this is valid functional dependencies to be in 3NF. X contains A, that is A is subset of X, meaning X determines A is a trivial functional dependency, or X is super key. If X is super key, also it is valid. This kind of functional dependency can exist in 3NF. If X can be super key and it can determine any other attribute, it is also valid. Or in the previous case we have seen A can be subset of X. A can be subset of X, or every element of A minus X. If we do A minus X, the set difference between A and X is a prime attribute. That is, each attribute in the A minus X contained in the some candidate key. So let us say A, previous example only, employee ID, employee name, together determining employee name. So what is our X? X is this one. What is our A? Employee name. If we subtract A minus X, if I do E name minus, no, then this should be something longer. No, this should have some longer. I will take example from here itself. Okay, let us see this example here. This table, book table. I'm just to explain the 3NF, I'm taking this example from our the slide only. So book table has book, genre, and author nationality. You can see these functional dependencies hold for this table. Book determines author. So for this 20,000, this author is Jules, this one. And for genre, this author, for journey, this to the center of the earth, for the other is this one. So this relation, this functional dependency is hold. So you can see for every book the author is different, and book determines author is true. This is valid functional dependent FD. And author does not determine book. You can see for Jules author, you can see book is 20,000 leagues under the sea and journey to the center of the earth. It should be the other way, like if it determines, if author determines book, then for each this author it should be always 20,000 only. It cannot be other things. So this functional dependency does not hold. And you can, and author determining, so you can see author determines author nationality. For this one, for Jules, author nationality is French. For Walt, the nationality is American. For Leo, it is Russian. So this holds. This FD holds for this schema or this table. So author determining author nationality is true. So what is the primary key here? What is the primary key of our table? So book is the primary key, right? Book determines author and author determines the nationality. So if we take book closure, then we will get a book, author and author nationality. So book is the primary key of our table. Are you following, everyone? If you have any doubt, please ask. Following, right? Any
Yes,
doubts?
ma'am.
Okay.
Yes, ma'am.
Yeah. So what is the primary key here? Book. Book is the primary key. It determines author and author determines author nationality. If you see here, what are prime attributes for this table? The prime attribute, the candidate key is only book. It is only book. Let us see this FD. Book determines author. It is valid because X is primary key. X is primary key. Book is primary key. X determines A. X is super key or candidate key. Here it is candidate key. So it is valid. This is valid. And this, if we see this dependency, author determining author nationality. What is author and what is author nationality? Both are non-prime attributes. Non-prime attribute is determining another non-prime attribute. So this is not in 3NF. This relation is not in 3NF. If we get this kind of uh, dependency in our relation, then this won't be in 3NF. The other way, alternatively, we can check for 3NF by seeing. So we can do A minus X. That's what it is given. No, A minus X we can check. So author nationality minus author is only author. Author, right? Is author part of candidate key? Is author part of key? No, author is not part of key. So this is not in 3NF. In the other way also you can check. You can check whether we have non-prime attribute determining non-prime attribute, or we can check, we can just take A minus X. A, we can do set difference of A minus X and see whether the result is part of candidate key. If it is not of key, part of candidate key or anything, then we can say the relation is not in 3NF. Okay, a relation which is in 3NF is naturally it will be in 2NF. Okay, for these are the conditions you everyone understood, no? These conditions for a relation to be in 3NF, it should be in 2NF first. That means it should not have any partial dependency. And like if we have any functional dependency, X determines A, then the functional dependencies can be trivial. That means A can be subset of X, or X can be super key. It can be super key of R. Then we can say it is in 3NF. And if we do A minus X, after doing A minus X, and if it is part of the candidate key, then if the result is part of the candidate key, then if any one of the conditions holds for our FDs, then we can say our table is in 3NF. If one of them is not, if they are not satisfied, if any one of them are not satisfied, like X, like A is not subset of X, or X is not super key, or A minus X is not part of candidate key, then we can say the relation, if any one of these conditions are not satisfying, then we can say our relation is not in 3NF. Okay. Okay, I have already explained this. A transitivity dependency is a functional dependency which holds by virtue of transitivity. A transitive dependency can occur only in the relation that has 3 or more attributes. If we have 3 or more attributes, then only the transitivity dependency is possible. Let us see here example. Let A, B, C designate 3 distinct attributes, or or distinct collection of attributes in the relation. Suppose all three of the following conditions hold. If A determines B is true, and it is not the case that B determines A, and if B determines C, like A determines true, B is true, and B determines A is false, and B determines C is true, then by rule of transitivity, we can write A determines C, right? Then the functional determines dependency A determines C holds, which follows by the axiom of the transitivity. Okay, that is just to explain what is transitive dependency. Okay, example. This is example. Here you can see supplier city has supplier ID status city. What are FDs true for this relation? For this relation, what FDs are true? SID determines status, SID determines city is true because SID is a primary key. And will status determine anything? And you can see city. For Delhi it is 30. For Delhi it is 30. So yeah, status, that city determines status is also true. City determines status is also true. Okay, is there any transitivity dependency? Like non-prime attribute determining another non-prime attribute exists, right? Here you can see these functional dependencies false, and city determining status. City is non-prime attribute which is determining any other non-prime attribute. This one status. So this is not in 3NF. As we have seen, this functional dependency, it is not in 3NF. Transitivity dependency exists. You can check for 3NF, like if non-prime attribute determining another non-prime attribute. If that dependency exists, then we can say that is the relation is not in 3NF. Or you can check A minus X you can do. So status minus city is status, and you can check whether status is part of candidate key. No, status is not part of candidate key, only SID is there. So it is not part of candidate key. By this way also you can check. So this relation is not in 3NF. Okay, how can we decompose it? We can just city and status, we can keep that in the one table, and the other things SID status, SID, sorry, what are the other things? So city and the status can be in one table. So whatever the FDs holds here, you can see SID status is true, SID city is true, and city status, this can be in the one table. And the other table what we can keep SID and city, because already city determines already status. That information is true. That information is valid, no? That is we are storing. So city already determines status. City is already determining status. So that information is already stored. So SID determines city, we will store in the other table, and SID and status will be kind of not required because city is already determining the status. Okay, we will see the rules, how to decompose, like the rules for decomposition. If we have some schema, if we wanted to decompose it into 3NF or 2, or BCNF, we will see how to do that in the later slides. And the above two relations are in, these are lossless join, 3NF, and their dependency preserving. So this is an example. For 3NF, you can see the relation department advisor with the attributes SID, IID, and department name, and this FDs holds for this relation SID comma department name together determines IID. So what is our primary key here? Our primary key is SID department name together, right? SID department together are the candidate key. Let us see. Like SID alone is not primary key because it is not determining anything. IID alone cannot be primary key because it is not determining SID. So SID department name together form the candidate key, and these dependencies is SID department name determining IID is valid dependency because X is candidate key, or it is like you can X is candidate key, and IID determines department name. So it is valid, right? It is not like non-prime attribute determining non-prime attribute. IID is part of department name. Okay, wait, I will just tell this. So if you do department name minus IID, what we will get? We will get department name. Department name is part of our candidate key, right? Department name minus IID, if I do set difference of A minus X, and the result is the candidate key. Result is part of candidate key. So it is department name. We will get department name minus IID is department name, and department name is part of candidate key. So this is in 3NF. This is in 3NF. So you can check for if non-prime attribute determining any other non-prime attribute. No, right? This is IID is non-prime attribute, but it is determining prime attribute. It is determining prime attribute. So this is not there. So this is like in 3NF. The relation is in 3NF. You can check it in two ways. Okay. Understood everyone how to check for 3NF, whether the schema is in 3NF? Yes or no?
Yes, ma'am.
Okay. In 3NF also some redundancy is possible. The same example, it is shown in the table, but for J it is denoted as SID, for SID it is denoted as J, and for IID it is denoted as L, and department name is denoted as K. And if you see this table holds the dependencies which are mentioned above, like SID department name together determines IID, that is true, and IID determines department name, that is true for this table. JK determines L and L determines K. But you can see this one, L1 K1 L1 K1 L1 K1, redundancy is there. The repetition of the information, for example, for the relationship L1 K1, that is IID and department name, the what redundancy is there, and we need to use null values, for example, to represent L2 K2 where there is no corresponding J, where there is no corresponding SID. For that we have to represent that using the null values if there is no separate relation. Okay, the thing is in 3NF also some kind of redundancy will be there, but our decomposition will be lossless join and the dependency preserving. So some redundancy will exist in 3NF also. Okay. Okay. Everything, anything, any doubts? 1NF, 3NF, 2NF.
No, ma'am.
Okay. We can see 6.2. So here we'll study the algorithms to decompose our relations into 2NF or 3NF. So we'll study the decomposition algorithm for relation to 3NF or BCNF. So yeah. The 3NF decomposition motivation is there are some situations where BCNF is not dependency preserving. So there are some situations where BCNF is not dependency preserving, and efficient checking for FD violation on the on updates is important. So this is like it. So what are the desirable decomposition properties we have seen? It must be lossless, and it should be like kind of dependency preserving also. But BCNF does not preserves dependency. So solution is to go for weaker normal form, which is 3NF. 3NF will allow some redundancy. We have seen in the previous table, it allows some redundancy, but it preserves. It is like this is always 3NF is always lossless join and dependency preserving decomposition. This is the motivation for 3NF, why we are going for 3NF. A relation scheme, okay, we have already seen this is kind of repetition, same thing. If it is in 3NF, and if this FD is true, X determines A is true, then either A is subset of X, or X is super key, or X is part of candidate key. This we have already seen. And testing for a 3NF, we have already seen how to test whether a schema is in 3NF or not. Like we can check whether non-prime attribute determines non-prime attribute FD is there, or we can check whether X minus A we can do. If X determines A, we can do A minus X and see whether the result is part of candidate key. If it is not part of candidate key, then we can say the decomposition is not in 3NF. That The schema is not in 3NF. So how to, this is, if we have a table which is, we have a relation which is not in 3NF, if we wanted to decompose it into 3NF, if we wanted to decompose the relation into different tables which are in 3NF, how to do that? This is algorithm that defines that given a relation R, given a relation R with set f of fd functional dependency, with some set functional dependencies, find the decomposition R into set of 3NF relation Ra. So we can decompose that relation R into Ra, like multiple relations which are in 3NF. What is the algorithm? The algorithm is eliminate redundant FDs. First find the canonical cover, resulting in the canonical cover FC or F. So we have to eliminate all the redundant FDs, find canonical cover for our for our existing relation, and create a relation Ri equal to xi, xy for each fd. After getting canonical cover for our relation, our fd set, we can, for each and every relation, let us say x determines y, we can decompose that into one table. We can decompose that in one table xy. If the key, if our key is not present, if the key K of R does not exist in any relation Ri, create one more relation Ri equal to K. We can then form, just create one more relation with that key. Okay, so just find FD. After getting FD, we will get some functional dependencies. No? For each functional dependency, we can decompose that into one table. And if the key is not present in any table, we finally create a table for that key. That's all. The same thing is explained using this one. This, and upon decomposition, we will get each relation schema. Each of our decomposed table will be in 3NF, and this will be dependency preserving and lossless join. Okay, let us see an example here. We have this customer banker branch table relation with this attributes: customer ID, employee ID, branch name, and type. So these are the together, customer ID and employee ID together form the primary key, and these FDs holds. It is given these FDs holds for this table. So customer ID, employee ID determines branch name type. So this X determines a X is candidate key. No problem. This is valid FD to be in 3NF. Employee ID determines branch name. Okay, this is also valid because employee ID is part of key and it is determining another non-prime attribute. It is not like non-prime attribute. Okay, it is okay. Let us see. Customer ID branch name determines employee ID. If we see whether this relation is in 3NF or not, first check whether relation is in 3NF or not. How to check whether the relation is 3NF or not? The first FD is valid, we can tell, and the second FD, what we can do, we can say branch name minus employee ID. If we do, so we'll get branch name, right? We'll get branch name. Is branch name part of primary key? No, branch name is not part of primary key. This cannot exist. This cannot, this cannot be, this kind of FD should not be in 3NF. So this the given relation is not in 3NF. Not in 3NF. You understood now why it is not in 3NF? By seeing this FD, we can tell branch name minus employee ID. If you do set difference, we'll get only branch name. And branch name is not part of candidate key. Our candidate key is customer ID and employee ID, not a part of candidate key. So this is not a valid FD. If I subtract employee ID minus customer ID, branch name, employee ID is there. Employee ID is part of candidate key. This FD is valid to be in 3NF, but this is not valid to be in 3NF. Okay. So we understood this is not in 3NF and we have to decompose it into 3NF. So in order to decompose, first we have to find FC, canonical cover, for our decomposition. What is our canonical cover? You can see employee ID determining branch name. Here customer ID, branch name together, employee ID. So what is redundant here? Any attribute, this FD is redundant or not? It is redundant, no, kind of. Or you can just say, by seeing this branch name, just make the LHS like one attribute. We can see branch name here, it is redundant. Because employee ID determines branch name. Customer ID, employee ID together determines branch name is kind of, here it is extraneous attributes. Branch name is extraneous attributes. If I remove branch name from here and if I compute what closure of customer ID and employee ID, we will get the same branch name and type. So this branch name is an extraneous attribute here. So we can remove branch name, and final attributes at what we have now. After removing this branch name, we will have customer ID, employee ID determines type, employee ID determines branch name, and customer ID branch name determines employee ID. Is any FD redundant? Is any other FD redundant here? So these are our this one, no? After removing branch name. So if I remove this FD&C, if I remove this FD&C, just see, then can we get employee ID? Employee ID determines branch name. No, this is required, no? How to determine employee ID? By using customer ID and branch name. So this is required, and employee ID and branch name is also required, and this is also required. Any other FDs we cannot remove. Just to see any other FDs we can we remove? No, we cannot remove any other FDs. Is it clear? How to find canonical cover? First, we will remove the what extraneous attribute. After removing the attributes, we will see whether any FD is redundant. If it is not redundant, then we will get our FC canonical cover. Here, after removing the extraneous attribute branch name, all FDs are valid. There is no redundant FDs. Any doubts?
Ma'am, why is customer ID important in determining employee ID, ma'am? Here.
Which one? This
The
third dependency.
third. Yes, ma'am. Third one.
Yeah, because it is mentioned, no, customer ID branch name together determines employee ID. Customer ID alone cannot determine employee ID. It is given for this FD is given for us. If it did, see what we can do. How to find extraneous attribute? In order to find the extraneous attribute, what we will do? Just to make our LHS as, here we have branch name type, no, we'll just remove branch name or type and see whether which is redundant or not, just to make our dependency as single attribute. So if x determines a, here the same example, customer ID, employee ID, just to check after removing branch name and see the closure, customer ID, employee ID closure. If we take, are we getting branch name? Yes, we are getting branch name by using the other FDs we have. Okay, so we can remove this branch name, which is extraneous attribute. And okay, now we can go for LHS side. Let us remove employee ID from here and see, are we getting type? No, we cannot get type because customer ID, employee ID together determine type. So employee ID is required here. And here also same thing. If we remove customer ID or branch name here from here and see whether we are getting employee ID or not. If we just take the closure of branch name, then we will get only branch name because customer ID and branch name together determining employee ID. It is mentioned, right? If we remove here from here, if I remove customer ID, then are we getting, by taking branch name closure, are we getting employee ID? No, we cannot get employee ID. Branch name determines only branch name. So here customer ID is also required to determine employee ID. So this is how we find the extraneous attribute. So just wherever there are two attributes here two attributes, no, just eliminate one attribute and check, are we getting this closure? By finding this closure, are we getting this branch name also? If we get, then branch name is extraneous. If it doesn't get, then branch name is required. The same for LHS side also. If we remove employee ID and see, after removing employee ID and see, after removing employee ID, if we just check whether customer ID determines type by using the other FDs. No, customer ID and employee ID together determines the type. Customer ID alone cannot determine the type. So that's why employee ID is also required. It is not extraneous. Okay, that's how you find the extraneous attributes. First, make LHS as one. Like LHS and RHS, just remove. If we have multiple attributes, remove one attribute and check the closure of your right hand side and see whether we are able to determine the removed attribute using our FDs that we have already learned, right, in the previous week. The same thing. we, after finding the canonical cover, let us see are there any redundant FDs, like if the same, if we get same FDs like customer employee ID determines branch name, if we get the same FD here also, then we can remove that FD. So just find canonical cover, first to find the extraneous attribute and remove the extraneous attribute, and then see are any FDs redundant. If they are redundant, remove that. Here no after finding canonical cover, you can see like after finding extraneous attribute, you can see no FDs are redundant, so all are required. So now what we do, what we have to do in order to make this one in 3NF, what we have to do, we have already seen if there is some dependency x determines y, then we have to decompose it into a relation xy. So we can just decompose customer ID, employee ID type in one relation, and employee ID branch name in another relation, customer ID branch name, employee ID in another relation. After decomposing, we have to check whether primary key is present in any table or not. Yes, what is our primary key before decomposition? Customer ID, employee ID. We have this decomposition, customer ID, employee ID type in one table. Okay, now no need to create any separate table for our primary key. That's what what is our decomposed thing? It will have customer ID, employee ID type, customer ID, branch name, employee ID. That customer ID. uh, okay, you have observed that customer ID, employee ID type contains a candidate key for the original schema. Okay, it contains the original schema, so no further relation schema needs to be added, right? That we have seen. And at the end of for loop, delete and deduct the schema such as employee ID, branch name. So why employee ID branch name has to be repeated? Because this is already there. Because this is already we are storing employee ID and branch name. That's why just remove the subset, which is subset of other schemas, right? This is subset. This schema is subset of other schema. We will remove the redundant schemas here. Okay, after this is our decomposition for each xy, for each dependency x determines y. We have made our tables. This one xy, we have made separate tables: customer ID, employee ID type, employee ID branch name. All these dependencies x determines y, we have decomposed it into three tables. After decomposition, what we are checking, whether our tables are subset of any other table. If you see, employee ID branch name is subset of this table, customer ID, branch name, employee ID. So this table we can delete. And now what are our tables now? Valid tables: this one, customer ID, employee ID, and this table. So what, observe that customer ID, employee ID type contains candidate key. Yes, we have candidate key also in our decomposed schemas. So no need to create separate table for our candidate key of the original schema. So for no further relation schema needs to be added for our candidate key. And at the end, after decomposing, we have to check whether any table, whether any our decomposed table are subset of other schemas. Yes, employee ID branch name is subset of other schemas, so we can remove that subset table and our result will be this one. Okay, how to find? So first check whether it is our given schema is in 3NF. In order to check, we will find non-prime attribute determining any other non-prime attribute is there or not, or like candidate key like x minus a minus x. If you do, if x determines a, fd is there, then if you do a minus x, and if you get any part of candidate key, then it is okay. If it is not there, then the schema is not in 3NF. If a minus x if you do, and if it is not a, if it is not part of candidate key, then the relation schema is not in 3NF. We can decompose it into 3NF by using this one, by just whatever FDs we have. First we will find the canonical cover for that FDs, and after finding the, how to find the canonical cover, first eliminate the extraneous attribute and see whether there are any redundant FDs. If there are any redundant FDs, then we just hold one of them and eliminate the other one. Okay, and after finding FC canonical cover for each and every FDs, for each and every FDX determine A, we will create one relation. We will just write R1XY. For all FDs in the canonical cover, we'll create the separate relations For all the FDs, we'll create each and every relation. And finally, we will check whether the candidate key is present in the decomposed relation or not. If it is not present, we will create separate relation for separate table for that candidate key. And after doing all these things, after getting our decomposed relations, we'll see whether any relation is subset of any other relations. Here example here is employee ID and branch name is subset of this customer ID, branch name, employee ID table. So this is we can this table we can eliminate, and our result will be this one only, this 2D one. Okay, understood about TNF? Any doubts?
No, ma'am. Got it.
Okay. Others? I think if you solve questions, then you will understand more. These are some practice problems for 3NF, and we'll see BCNF now. 3NF you all understood, no? The other highest now 1NF, 2NF, 3NF. The next highest normal form is BCNF. Boise called normal form. Okay. A relation schema R is in, you understood, right? How to decompose a table to 3NF using that algorithm. Yeah. A relation schema R is in BCNF with respect to set F of FDs if for all FDs in F plus of the form alpha determines beta, where alpha is subset of R and beta is subset of R, at least one of the following holds. Like if there is some FDs in our given FD set, if at least one of the following condition holds, we can say it is in BCNF. The relation is in BCNF. So alpha can be like beta can be subset of alpha. Beta can be subset or equal to alpha, which is trivial functional dependencies. Then this will be in BCNF. Okay, if this relation is there, then it's okay. If this FD is there, this is okay. And if alpha is super key or beta, then also we can say this is in BCNF. So if for all FDs for a given relation, if we have some relation R, if we have set of FDs for the given relation, at least one of the following condition should hold. Like alpha should determine beta. If alpha determines beta, for example, this is one FD. If this relation has to be whole, if this relation has to be in BCNF, it should satisfy this condition, whether like beta must be subset of or equal to alpha for FD, or alpha must be super key. If this condition holds for the given FDs, then we can say our given relation is in BCNF. That means only these are the condition. It must alpha, one is trivial, like beta is subset of alpha, that is trivial FD, and the other thing is alpha determining beta, where alpha is super key. So if any one of the condition is satisfied for a given FD, for like if we have set of FDs 1, 2, 3, any one of the condition should be satisfied for all three FDs, then only we can say the relation is in BCNF. Clear? Like for a given FD set, at least one of the following condition should hold, like trivial functional dependency or alpha should be super key. Okay. This is example. This example you can check. Given FD, what is super key here? What is super key here for this relation? A determines B and BC determines D. So AC can be super key, right? If we say A, like candidate key. If I take AC closure, it will give A, C, B and BC together determines D. So AC will be the key. So A determines P. Is it valid? Is it valid FD to be in BCNF? No, right? Because A is not super key. A is not super key. It is not super key. So it is not in BCNF. And BC determined D also not valid FD to be in BCNF because BC is also not super key. Okay. Neither of the, you can see, neither of the dependencies in F contains only attributes of the form. So we might be misled thinking it is enough. In fact, AC determines D. So R2. Okay, here it is decomposed. You can see it is decomposed. This is not in BCNF, and we'll see an algorithm how to decompose our given relations to BCNF. We'll see algorithm. Just it has decomposed to A determines B, like one table AB and the other table is ACD. Just I will explain how the decomposition, how to do it, decompose to achieve BCNF later. But here example AC, it is given ACDE. Now check whether the decomposed thing is in BCNF or not. A determines B is valid because A is will be key, and it is valid to be in BCNF, and BC determines D. Are we getting this FD? In this decomposition, BC determines, no, we won't get, so it is not dependency preserving, it is not dependency preserving. Okay, we'll see that also. In fact, AC determines D. Yeah, AC determines the D is there in FD, shows that R2 is not in BCNF. Okay, if we get, see here A determines B, and we can write AC determines, I think that this is AC determines D. AC determines D is holding. Okay, what is our candidate key for this? We have E also. E is not there. E is not there. So ACE is our candidate key. ACE is not there. So this is also not in BCNF. Let us understand with more examples. Just this is a simple example. Let me just make it clear once again. Okay, we have relation with A, B, C, D, E, and with F. This FD said A determines B and BC determines D. So what is our candidate key for this relation? For this relation, it is, what is our candidate key? So just check on the RHS side. What attributes are not there in the RHS side? A is not there in the RHS side, and C is also not there in the RHS side, and E is also not there in the RHS side. You can see B and D are in the RHS side. So ACE must be part of candidate key. If I take ACE closure, then I will get A, C, E, and A determines B. So we'll get B, and by using B and C, we'll get D. So what is our candidate key here? It is ACE. Now we'll see our given FD set. Whether they are in BCNF or not, we have to check. How to check? Okay, let us take this A determines B. So alpha determines beta. If we have, then we have to check whether beta is subset of alpha. No, B is not subset of A. That is not true. That condition is not satisfied. We'll check other condition. What is the other condition? Alpha is super key or not? We have to check whether here A is super key. No, A is not a super key. ACE itself is a primary key. So it is A alone cannot be super key. So it is not valid. So it is in not in BCNF. So we are now it has, now this table has decomposed into two tables. AB has one table and ACDE in the other table. ACDE has other table. So AB relation is valid because alpha determines beta and alpha is super key. A is super key for this decomposed relation. This is valid to in B, this relation. This R1 is in BCNF. But R2, if you see, for R2, what is key? ACE. ACE is the key for R2. And B, this, if we check this dependency, BC determines D, this one, that can be, we can write it as by using ACD also. That we can write it as AC determines D by saying, just as A determines B, just replace it by, just do augmentation here. C, AC determines BC we can write, and by the rule of transitivity we can get AC determines D also. So I have written AC determines D. So what is key here for the decomposed relation R2? ACE. But here AC is determining D. Whether D is subset of AC? No, D is not subset of A. A. D is not subset. And whether AC is primary key? No, AC is not the primary key. ACE is the primary key. So our it is not in BCNF. Okay. Understood, right? It is not in BCNF. Got it or not? Yes or no? Hello?
Hello. Yes, ma'am.
Yeah, got understood now about BCNF. Just go
Ma'am,
for BCNF. Yeah. Okay. Now decompose it. What is the rule? In order to decompose our relation to be BCNF, what we can do? We can just to check if a relation Ri in a decomposition of R is in BCNF, just the same thing we'll do. We'll check whether alpha determines beta or whether alpha is super key or not. The same thing it is. If the condition is violated, then we can say it is not in BCNF. Okay. You can check this example also whether this is in BCNF or not. If it is not, the decomposed relations are in BCNF or not. You can check, and whether they are preserving dependencies also, we can check. Okay, the same examples. Should I explain the examples or should I tell how to decompose the relations into BCNF? Just let's see one example for now. We have relation R here with ABCD and this FD set. What is the primary key here? Just to take the closure, what will be the primary key here? Each and every attribute is a primary key, because A plus you take, then you will get A, B, C, D, A, everything, and B also. So everything is a primary key. So this is okay. This is okay. This is okay. So what is primary key here for this relation A closure? If you take A, B, C, D, will get B closure also will get B, C, D, and A, and yeah. So if we decompose the considering, we apply the above algorithm and check the result. By this is yeah. So this is in already in BCNF, no, the relation, because each and every FD, each and every FD is valid, because alpha is super key. Here alpha is super key only. Everything is a super key. But let us see. Here after decomposing, we have decomposed, here it is decomposed into A, B, B, C and C, D, and see whether the dependencies are preserved or not. Yes, their dependencies are also, yeah, just this is just to check whether the BCNF decomposition is preserving dependencies or not. Yeah, this thing already we have seen in the like last week only. The same example. This example is also same example to check whether the decomposition is dependency preserving or not. In the previous week's examples, we have seen already this decompositions. Okay, the rule for decomposing a relation into BCNF relations, like algorithm. This is algorithm. For all dependencies, A determines B in F plus, check if A is super key. If A is super key or not, we have to check by using the attribute closure. If A is not a super key, then choose a dependency in F plus that breaks the BCNF rule. Say A determines B. If it is not breaking the BCNF rule, like A is not a super key, neither B is not subset of A. The dependency is not trivial and it is not super key. A is not super key, that is breaking BCNF rule. Then what we have to do? We have to create a relation R1 by taking these attributes, whatever that are there in the FD, which is breaking the relation. So R1, we can create one relation R1 by having the together these attributes A, B, and we can create other relation R2 by saying R minus B minus A. So whatever the attributes that are there, the total attributes minus B minus A, we do. Then we get another relation R2. Okay. Note that R1 intersection R2 equal to A, that is A determines B. So this is lossless joint decomposition. Here if we do, so in this example we have attributes only A, B, right? Yeah. Okay, I will show example also. Here there are just two attributes, so not shown here. Okay, repeat for R1 and R2. After getting this one, R1 and R2, like R1 will be in BCNF for sure. For R2, we have to again check whatever dependencies holds for our R2 table and see whether they are following the BCNF rules or not. If they are not following, again decompose which are breaking that rules, again decompose whatever MD that are breaking those rules. Okay, let us see the example here. Okay, let us see here. A, B, C, this relation, we have this FD set. A determines B and B determines C. What is our key? A. A is key. You can clearly see A is key. Okay. Is A determines B is valid FD and B determines C is not valid because alpha is not super key, B is not super key. So what we can do, we can decompose it into AB. Whatever what is violating the BCN of this FD, no? So we can decompose R1 as BC and R2 can be like R minus B minus A. What is like R minus, what is our B here? C minus B. What is our ABC? ABC minus C, we will get AB. So whatever decomposed relation will be BC and AB. Okay, so let us see now. BC is in BCNF because B is super key and AB is also super key. A determines B is also valid. So our decomposition is in BCNF. So other example you can check. You can check this example also. The class, it has this many attributes: course ID, title, department name, all these attributes, and these are the FDs. So let us see what is the primary key here first. What is the candidate key? Course ID determine title, department name, credits, and building room number determines capacity. Okay, course ID. What attributes are not there in the RHS side? Just to check. Building room number, time slot, capacity. Okay, so what attributes are not there? Course ID is not there in this RHS side, you can see. And any other attribute? Section ID is also not there. ID is also not there in the RHS side. Semester year is also not there in the RHS side. So what is the primary key here? So course ID, session ID, semester year is the primary key. Right? If you take the closure of the course ID, session ID, semester year, then we'll get this all attributes. Building we will get, room number we will get, time slot we will get. Using building room number we will get capacity, and using course ID we will get title, department name, and credits. So our candidate key is course ID, session ID, semester year. And let us see whether this our FDs are in, whether this relation is in BCNF or not. How to check whether the relation is in? Just check the FDs. So you can see course ID alone determining this one is not in BCNF. This is not in BCNF. So we can decompose it into relations. So we can decompose course ID, title, department name, credits as one relation, and the other relation can be like all the attributes minus B minus A we have to do. So what is our B? Title, department name, credits minus course ID. If we do, then we'll get total title, department name, credits. So out of all our this attributes of our relation, if we remove title, department name, credits, then what we will be left with? So we'll be left with course ID, section ID, semester, year, building, room number, capacity, time slot. So our relation R1 will be this one, and the other relation R2 will be this one. So let us see what dependencies hold for this relation. So this is already in BCNF. Because course that this is primary key for this relation. So building room number determines capacity. This is not in BCNF, and you can see these attributes are present in this our the second relation, and this is not true because building room number is not primary key. The primary key is this one. So we can decompose it into building room number, capacity as another relation, and out of this relation, out of the decomposed relation, this one we can subtract building room number. Okay, sorry, we have to subtract B minus A. What is our B? B is nothing but capacity. Capacity minus building room number we'll get only capacity. So R minus capacity, if we do, just remove capacity from here. And make building room number, capacity as one table. And if we remove the capacity from here, we'll get other table. So other table will be course ID, section ID, semester, year, building, room number, time slot. So the decomposition will have building room number, capacity as one table, this one for one table, and the other table will be course ID, session ID, semester, year, building room number, and time slot. Just we have removed capacity. Okay, that's all. Now let us see the FDs are in BCNF or not. Building room number, capacity is in this one, this FD will hold, and this is will be in BCNF, because this in this the primary key, in this the primary key is building room number, and this is determining capacity. Alpha is super key, this is valid. And here also the other FD, course ID, session ID, semester year is a primary key of our relation, and it is determining the other attributes. This is also valid. So the decomposed relation will have three tables. One is this one, course table, that has course ID, title, department name, credits. And the other is classroom table, it has building, room number and capacity. And that session table, which has the remaining attributes. So this is an example for BCNF. Another example, just to see whatever the dependencies which are violating BCNF. So that violating dependency we can create, make it as one table, and the other table could be R minus, let us say alpha determines beta. Then we can write this is breaking BCNF rule. Then we can create R1 as alpha beta and R2 as R minus beta minus alpha. So R, like let us say R has many things, alpha, beta, gamma. Then R minus alpha, beta, gamma minus beta will give us what? Alpha, gamma in other table. So we have to do this. For every BCNF breaking decomposition, we have to just create one table, and the other table can be R minus beta minus alpha. After decomposing this table, for this table we have to check whether it is in BCNF or not. The dependencies, whatever dependencies holds for this table, the dependencies we have to check whether they are following BCNF rule or not. If they are not following, again same thing. Which whatever table which is not following that BCNF rule, that table we have to decompose. That dependencies we have to decompose into one relation, and the other relation can be R2 minus whatever that is violating, let us say beta 2 minus alpha. So we'll get R2 minus beta 2. The other, in the other table we will get the other dependencies other than beta 2. Okay, understood or not? Yeah, if you have any doubt, no, please ask. Okay.
Ma'am, sorry to interrupt. Just wanted to know, today's session is not there, no, generally weekly.
It's not there weekly. It is an extra session because you have deadline, no, like submission deadline. Week
Okay,
6
ma'am.
and week 7 both has to be covered. That's why.
Okay, right, ma'am. Okay.
Yeah, it is not possible always to get PCNF decomposition that is dependency preserving. So we have already discussed 1NF, 2NF, 3NF. All decompositions are dependency preserving and lossless join decomposition. But but for BCNF it is not always possible to get dependency preserving decomposition in BCNF. Let us see an example here. This one example. We have our JKL with attributes JKL and this FD set. So what is the key here? What is our key here? What is there not there on the LHS side? Not on the RHS side, J is not there. So J must be a part of E. Let us take J closure. Only we will get J. Now if we say JK closure, then we'll get JKL. So JK is our key. And let us take JL also. JL also. Then because L is determining K, no, we'll get J, L and K also. So these are the candidate keys, JK and JL. Okay, now see whether this R is in BCNF or not. So JK determines L. That is okay because it is key. It is okay. It is in BC. This is like holding that property. Okay. L determines K. L is not key. L is not key, and K is not subset of L. So this is not. This is violating BCNF. And how to decompose? We'll decompose LK as one table, and in the other table we will get J K, L, these are our attributes of our R minus K. If we do beta minus alpha, that means K minus K, then we will get what we will get JL. JL will be in one table and LK in the other table. So what FDs holds now? What FDs hold? Only L determines K we will get, determines K we will get, and how to get JL determines K. How to get JK determines L? Can we get JK determines L? This one? L determines K we are getting, but JK determines L are we getting in the decomposed tables. What updates will occur here? L determines K, and we have to check whether JK determines L in any way. We cannot get that FD, no? That FD we cannot get. JK determines L, that FD we cannot get because it is not preserved. Not after decomposition, this FD we cannot get. So any decomposition of R will fail to preserve JK determines L. So it is we are not getting this FD. This implies that testing for JKL requires a join. Okay. So that means the BCNF decomposition, it is not possible always to be dependency preserving. There can be, we can get the decomposition which BCNF decomposition which does not preserve the dependencies. Okay. Okay, this is the trade-off between BCNF and this one 3NF. Okay, it is always possible to decompose a relation into set of relations that are in 3NF, such as decomposition is lossless and dependencies are preserved. And it is always possible to decompose a relation into set of relations that are in BCNF. If we have relation, we can decompose our relation into either in 3NF or BCNF. But the 3NF always guarantees lossless and dependency preserving decompositions. But BCNF, the decomposition is lossless, but it may not be possible to preserve dependencies in case of BCNF. This is the difference between 3NF and BCNF. It concentrate on the primary key, 3NF concentrate on the primary key, and it can concentrate on the candidate key, BCNF. Redundancy is high compared to BCNF. In case of 3NF, redundancy is high. In case of BCNF, there is no redundancy, but it preserves all the dependencies. 3NF will preserve all the dependencies. BCNF will not preserve the dependency. Okay, this is already we have discussed. A dependency X determines Y is allowed in 3NF if X is super key or Y is part of some key. A dependency X determine Y is allowed if X is super key. That is the difference between 3NF and BCNF. So there is a trade-off. If some redundancy is permitted, okay, then we can go for 3NF, which preserves all the dependencies. But if we don't want any redundancy, then we can go for BCNF. But they may not preserve dependencies. This is the trade-off between BCNF and 3NF. Okay. That's all about lecture 6.2. And lecture 6.3 is about some example. Is it clear BCNF decomposition, everyone? Whatever I have discussed till now, is it clear? Yes or no? Any doubts? Yeah, you can ask any doubts if you don't have. And is it clear or not? Okay. And yeah, this one and lecture this one third lecture is about some example only. You can just go through that example. Okay, the lectures 6.4 and 6.5 is about MVD and 4NF. That you can see that will be discussed in the next session. Okay, meanwhile, if you have any doubts, from these topics, 3NF, 1NF, 2NF, and BCNF, like how to check for that, whether relation is holding that, is in that normal form or not, or how to decompose if it is not, and how to decompose our relation into that normal forms. If it is not clear, you can ask, and just for understanding you can practice some examples from our anyone of you have tried solving the examples, this one practice assignment examples? Do you have any doubts?
No, ma'am.
Okay, just we'll see one example. Just try to solve the first question. I will give some time and just solve the first question. Here, consider the relation schema R with these attributes A, B, C, D include only atomic values. That means it is in 1NF. Identify the possible set of functional dependencies that are that R can have such that R is in BCNF. So identify which are in BCNF, which FDs follows BCNF. This is simple only, no? Just we can. And this is not MSQ, this is only MCQ. Just try, I will give some time. Just will solve first two problems, okay, so that time also will be finished. Tried solving it. Solved. Yeah, let me know once you are done. Okay. Solved, yes or no? Okay, I will discuss this question. So AB, what is the key here? What is the key for this? At given FD set, if you take closure, AB closure, then AB is a key. AB determines A, B, and C, D, E. So it is a key. It is candidate key, and it is determining C, D, E. So this is alpha determines beta, and alpha is super key here. So it is valid FD to be in BCNF. This is correct answer to be in BCNF. And if we see the other FDs here, AB determines CD and B determines E. What is key here, which is not there in the RHS side? AB. AB is not there in the RHS side. If you take AB closure, it will determine AB and CD. And it also B determines E also. Yes, this is also AB determines CD. What is our key here? AB is key. Right, AB determines CD is valid because AB determines A, B, C, D, and E also. From B we will get E, and B determines E. Whether B is key, B is not a key. AB together is a key. So this is this FD. B determines E is violating BCNF. So this is not correct answer. And if you take the other, this one third option, AB determines CD, and just to find the key. How to find the key? Just take the attributes which are not in RHS side. AB is not in RHS side. If I take AB closure, we'll get AB, CD, and from D I will get E also. So AB is the key. If I just check, now I have to check whether alpha determines beta, whether alpha is super key or not. No, here C determines C and determines E. They are not alpha. C is not super key and D is not super key. So these are violating. These two FDs are violating BCNF rule. Now the fourth option, AB determines C, D, E, D determines A, and A determines B. Let us do what is the candidate key here, which is not there in the RHS side. So everything is there in the RHS side. So just check whether AB by taking A, Just check by taking D. Okay, we'll do D. If I take D closure, I will get DA. That's all. If I take E closure, I will get only EB. If I take AB closure, I will get A, B, C, D, E. So AB is a key. AB is a key. And whether D determines here, D determines A and D determines B. These are not valid. F is to be in BCNF because D and E are not super keys. Just check the answer. Okay, that is correct. Okay, that's all. If you have any doubt, you can ask. Any doubt? Is it clear? The question, first question. Yes or no?
Yes, ma'am. Clear.
Okay, just to we'll solve the second question and we'll close the session. Just try to solve the second question.